Welcome to DAR Tutors. Today, we're diving into one of the most important concepts in all of statistics, the normal distribution. This lesson is specifically designed for IB mathematics analysis and approaches higher-level students. By the end of this video, you will be able to, first, understand and describe the key properties of the normal distribution curve. Second, apply the empirical rule to estimate probabilities within 1, 2, or 3 standard deviations of the mean. And third, use a graphics calculator to find any normal probability. Let's begin by introducing this crucial statistical model. The normal distribution is a fundamental type of continuous probability distribution. It's often called the Gaussian distribution after the mathematician Carl Friedrich Gauss. Its most recognizable feature is its symmetrical bell-shaped graph. We represent it as a probability density function, or PDF, because for continuous variables, we calculate the probability of a range of values rather than a single exact value. The normal distribution is incredibly useful because many naturally occurring phenomena closely follow this pattern. Think about things like the heights of people, the scores on a standardized test, the weights of a product from a manufacturing process, or even the measurement errors in an experiment. In each of these cases, you'll find that most values cluster around an average or mean, and as you move further away from that mean in either direction, the values become less and less frequent. So, the most common values are those in the middle, near the peak of the bell curve, and the extremely low or high values in the tails are rare. This pattern is what we model with the normal distribution. It describes how values in a population are spread out around their average. So, how do we define a specific normal distribution? Every normal distribution is characterized by two key parameters. The first is the mean, represented by the Greek letter mu-m. This measures the center of the distribution. It's the point where the bell curve peaks. The second parameter is the standard deviation, represented by the Greek letter sigma, samu. This measures the spread or dispersion of the distribution. A small standard deviation means the data is tightly clustered around the mean, resulting in a tall and narrow curve. A large standard deviation means the data is more spread out, leading to a flatter and wider curve. If a continuous random variable, let's call it x, follows a normal distribution with mean m and standard deviation c's, we use a specific notation. We write it as x is distributed as n of m, sigma squared. The squiggly line is read as is distributed as. It's very important to note that the second parameter is the variance, which is sigma squared, not the standard deviation itself. Be careful with this, as it's a common mistake. Now let's explore the mathematical definition of this curve, its probability density function. You are expected to be familiar with this formula. The function is f of x equals 1 over sigma times the square root of 2 pi, all multiplied by e to the power of negative 1/2 times the quantity x minus mu over sigma squared. While you won't typically be expected to manually compute values using this formula, you must understand the properties this function implies. First, the curve is perfectly symmetrical about the vertical line x equals m. This means the mean, median, and mode are all the same value. Second, the function f of x is always positive. This makes sense, as a probability density cannot be negative. Third, the x-axis acts as a horizontal asymptote. The tails of the curve approach the x-axis but never actually touch it. Fourth, the maximum point of the curve, its peak, occurs at x equals mesisi. Fifth, and this is a key one, the curve has points of inflection at x equals m plus or minus sigma. These are the points where the curve changes from being concave down to concave up. This means the standard deviation is the horizontal distance from the line of symmetry, x equals mu, to a point of inflection. This provides a geometric interpretation of sigma. Let's put our understanding of the parameters m and s into practice. Here's a typical IB question. We have 4 different normal distribution curves, A, B, C, and D on the same set of axes. Our task is to match each curve with its correct pair of parameters. Remember, the mean m determines the center, and the standard deviations determines the spread. Let's first identify the curves based on their mean. Curves A and B are centered around x equals 5. Curves C and D are centered around x equals 15. Now let's look at spread, or the standard deviation cis. We can use our knowledge of the points of inflection to estimate which curve has the largest and smallest sigma. Let's compare curves A and B, which both have a mean of 5. Curve A is much wider than curve B. This means curve A has a larger standard deviation. Looking at our options, C has S equals 1 and A has S equals 2. Therefore, A is M equals 5 and S equals 2, and B is M equals 5 and S equals 1. Now let's compare curves C and D, which have a mean of 15. Curve C is very wide and flat, while curve D is very narrow and tall. This tells us C has a large standard deviation, and D has a small one. Our options are S equals 0.5 and S equals 3. Clearly, D is M equals 15, and S equals 0.5, and C is M equals 15, and S equals 3. By comparing the centers and spreads of the curves, we can correctly match them to their parameters. So, to recap, mean shifts the curve horizontally, and standard deviation changes its height and width. So we've seen how to identify a normal curve and its parameters. But how can we use this to estimate probabilities? We can use the empirical rule, also known as the 68 to 95 99.7 rule. While this rule is a fantastic approximation, it's not perfectly precise. The exact percentages are 68.27%, 95.45%, and 99.73%. For most IB problems, these simplified percentages are acceptable unless otherwise specified. Let's break it down. First, approximately 68% of the data lies within one standard deviation of the mean. This means the probability that a randomly chosen value x falls between m minus s and m plus s is about 0.68. Second, about 95% of the data lies within two standard deviations of the mean. The probability that x falls between m minus 2s and m plus 2s is about 0.95. And third, approximately 99.7% of the data lies within three standard deviations of the mean. The probability that x is between m minus 3s and m plus 3s is about 0.997. This tells us that nearly all data in a normal distribution falls within three standard deviations of the mean. The symmetry of the curve is incredibly useful here. Because the mean is in the exact center, we can bisect any of these intervals. For example, if 68% of the data is between m minus s and m plus s, then half of that, or 34%, must be between m and m plus s. The same percentage, 34%, would be between m minus s and m. The IB often provides this diagram on the data booklet, which breaks down the curve into segments with their corresponding percentages. Using this diagram is the easiest way to solve problems involving integer multiples of the standard deviation. Let's look at this diagram. It shows that between the mean and one standard deviation above or below, there is 34.13% of the data. Between 1 and 2 standard deviations, there's 13.59%, and between 2 and 3 standard deviations, there's 2.15%. Beyond 3 standard deviations, each tail contains only 0.13% of the data. Knowing this diagram is essential for solving IB problems that test your understanding of the empirical rule. Let's apply the empirical rule to a worked example. Suppose the heights of a certain species of plant are normally distributed with a mean of 25 centimeters and a standard deviation of 3 centimeters. What proportion of plants would you expect to have a height between 22 and 28 centimeters? First, we need to express these height values in terms of standard deviations from the mean. Let's look at 22 centimeters. The mean is 25, and the standard deviation is 3. 22 is 25 minus 3, which is one standard deviation below the mean. So it corresponds to m minus s. Now for 28 centimeters. 28 is 25 plus 3, which is one standard deviation above the mean. This corresponds to m plus s. So the question is asking for the proportion of plants whose height is within one standard deviation of the mean. According to our diagram, the area between m minus s and m is 34.13%, and the area between m and m plus s is also 34.13%. To find the total proportion, we just add these two percentages together. 34.13% plus 34.13% equals 68.26%. So, approximately 68.3% of the plants will have a height between 22 and 28 centimeters. Let's do a slightly more complex part. What is the probability that a randomly selected plant is taller than 31 centimeters? Again, let's find our standard deviation value. The mean is 25, sigma is 3. 31 is 25 plus 3 plus 3, or 45 plus 2 times 3. So, 31 centimeters is 2 standard deviations above the mean, m plus 2 s's. We need to find the area under the curve to the right of this point. Looking at the diagram, the area from m plus 2s to me plus 3s is 2.15, and the tail area beyond me plus 3s is 0.13%. Adding them gives us 2.2, so the probability that a plant is taller than 31 centimeters is approximately 0.02. Only about 2.3% of plants will be this tall. The empirical rule is great for quick estimates, but what if the values we're interested in aren't exact multiples of the standard deviation? That's where technology comes in. The normal PDF f of x has no simple antiderivative. This means we can't solve probability problems by hand using calculus. Instead, we use numerical integration, which our graphics calculators are programmed to do for us. The key function to use is the normal cumulative distribution function, or normal CDF. On most calculators, you'll find it in the d-ester or stat menu. Let's work through an example using a calculator. We'll find the probability that a value x lies within a certain range. Suppose a normal variable x has a mean of 60 and a standard deviation of 5. We want to find the probability that x is between 62 and 67. First, find your normal CDF function. It will prompt you for 4 values. The lower bound is the starting value of your interval, 62. The upper bound is the ending value, 7. The mean m is 60, and the standard deviation s is 5. Note again that you must input the standard deviation, not the variance. After inputting these and pressing enter, the calculator gives us a probability of approximately 0.230. So there's about a 23% chance that a random value from this distribution will fall between 62 and 67. Let's quickly sketch this to visualize what we've calculated. The probability is the area under the curve between these 2 points. What if we need to find the probability that a value is greater than a certain number? Let's see how to set up the calculator for this. Suppose x is normally distributed with mean 28 and standard deviation 4. Find the probability that x is greater than 35. We need to find the area under the curve from 35 all the way to positive infinity. Since the curve is asymptotic to the x-axis, the area goes on forever. But we can't type infinity into our calculator. The solution is to use a very large number for the upper bound. A common practice is to use 10 to the power of 99, or 1 followed by 99 zeros. This value is so far out in the tail that the probability of anything occurring beyond it is essentially 0, so it's a very good approximation of infinity. So we set the lower bound to 35, the upper bound to 1e99, the mean to 28, and the standard deviation to 4. The calculator gives us approximately 0.04. Similarly, to find the probability that x is less than a certain number, we use a very large negative number, like negative 10 to the power of 99, for the lower bound. This approximates negative infinity. This technique of using very large positive or negative numbers to represent infinity is fundamental when working with continuous probability distributions on a calculator. Now let's tackle a more challenging problem, one that connects the normal distribution to the binomial distribution. This is a classic IB/HL level question. The times taken for students to complete a certain puzzle are normally distributed with a mean of 28.3 minutes and a standard deviation of 3.6 minutes. First, we're asked to find the probability that a single student takes at least 30 minutes to finish the puzzle. This is a straightforward calculator problem. We find p of x greater than or equal to 30. The lower bound is 30, the upper bound is infinity, 1e99. The mean is 28.3, and the standard deviation is 3.6. This gives us a probability of approximately 0.3184. Now for part B, where we bring in the binomial distribution. We select 10 students randomly. We want to find the probability that 5 or fewer of these 10 students took at least 30 minutes to complete the puzzle. Notice that we have a fixed number of trials, n equals 10, and we're looking for the number of successes. A success in this context is a student taking at least 30 minutes. We've just calculated the probability of success, p, which is 0.3184. This is the definition of a binomial distribution. So, let y be the number of students who take at least 30 minutes. Y follows a binomial distribution with n large 10 and p 0.3184. We need to find p of y less than or equal to 5. We use the binomial CDF function on our calculator, which calculates cumulative binomial probabilities. We input n equals 10. P equals our calculated probability of 0.3184 and the x value of 5. The result is approximately 0.938. This means there's a 93.8% chance that 5 or fewer students will take at least 30 minutes. This example beautifully illustrates how concepts are interconnected in HL mathematics. The normal distribution gave us the probability of an individual event, which then became the success probability for a binomial distribution involving a group. Let's work through another HL-style problem, this time focusing on finding the parameters mim and s when they are not given. Suppose the weights of oranges are normally distributed. We are given two pieces of information. 84% of the crop weighs more than 152 grams, and 16% weighs more than 200 grams. Our goal is to use this information to determine the mean m and standard deviation c. We'll solve this using the empirical rule. Let's start with the second piece of information. 16% of the oranges weigh more than 200 grams. This means the tail area is 16%. Here's our diagram. The area in the right tail beyond m plus s is 2.15% plus 0.13%, which is about 2.28%. The area between m and m plus s is 34.13%. The total area to the right of the mean is 50%. Now, where does 16% fall? Well, 50% minus 34.13% is 15.87%, which is approximately 16%. This tells us that the value 200 must correspond to m plus s. So we have our first equation. M plus s equals 200. Now let's use the first piece of information. 84% of the crop weighs more than 152 grams. If 84% is to the right of 152, then 100 minus 8%, or 16%, must be to the left of 152. This means the area in the left tail is 16%. By symmetry, this 16% must correspond to the value m minus s. So here is our second equation, m minus s equals 152. Now we have a system of two linear equations with two variables. Let's solve for MEP. Yes, if we add the two equations, we get 2d equals 352. Dividing by 2 gives us MDE equals 176 grams. Substituting this back into the first equation, 176 plus S equals 200, gives us S equals 24 grams. So, the mean is 176 and the standard deviation is 4. The second part of the question asks for the percentage of oranges weighing between 152 and 224 grams. We just found these are MEP minus SS and M plus 2S, respectively. The area between them is 34.3% plus 34.3% plus 13.59%, which is about 81.85%. This problem demonstrates how to reverse the process, using probabilities to find the parameters of the normal distribution, a crucial skill for more advanced IB problems. We've covered a lot today. Let's quickly recap what you've learned. You can now define a normal distribution, understand how the mean mu and standard deviation sigma determine its shape and position, and you can calculate probabilities using both the empirical rule and your graphics calculator. We've seen how to handle ranges, tails, and even how the normal distribution can interact with other distributions like the binomial. To solidify your understanding, here are 5 IB-style practice questions. Pause the video and try them on your own before I go through the solutions. 1. The mean score on a test was 68, and the standard deviation was 4. A student scored 72. In terms of standard deviations, how far above the mean is this score? 2. A normal distribution has mu 110 and sigma 5. Use the empirical rule to find the approximate probability that x is less than 105. 3. Given x is normally distributed with mean 20 and variance 9. Find P of 19 less than X less than 23. 4. Suppose X is distributed normally with mean 300 and variance 20 squared. Find P of X greater than 325. And 5. A machine fills cups with coffee. The volume of coffee X in milliliters is normally distributed with mu 240 and sigma 3. What is the probability that a random cup contains between 236.5 and 243.5 millimol? Let's go through the solutions. For question 1, the score 72 is 4 units above the mean of 68. Since the standard deviation is 4, this is exactly 1 standard deviation above the mean. For question 2, 105 is 1 standard deviation below the mean. 110, 5 equal 105. The area in the left tail is 16%, so px, 105, is approximately 0.1. For question 3, be careful. The variance is 9, so the standard deviation is its square root, which is 3. We use the calculator with a lower bound of 19, upper of 23, mean of 20, and standard deviation of 3. For question 4, x is distributed normally with mean 300 and variance 20 squared. We need the area greater than 325. Use a lower bound of 325 and an upper bound of 1e99. The result is about 0.106. Finally, for question 5, we use the calculator again with a lower bound of 236.5, upper of 243.5, mean of 240, and standard deviation of 3. This gives a result of approximately 0.770. Excellent work. You're now well equipped to tackle normal distribution problems in IB mathematics. Remember these concepts, and you'll be able to solve a wide range of questions. Thank you for watching DAR Tutors. For more in-depth explanations and tutoring, visit our website. See you next time.